know why you need FR, that's why. If you need to convince somebody why they're being asked to wear it, why they're being asked to pay for it, whatever, you're welcome to that video clip. You do not want to be the guy on the left. Stop, drop, and roll will not put that out in time to save you. Second-degree burn happens at these temperatures inside of a second. So that's not enough time in real time. You stop, drop, and roll, all right, maybe it doesn't burn for 20 seconds, maybe it burns for 5 seconds, but the damage has been done. What you may do is reduce the body surface area. You may reduce what would otherwise become third degree, but the damage is done very, very quickly. You don't want that happening. So back to TEEX. This little black dot, that is the same sensors that are in the mannequin in the official test. The silver around it is the wiring and the insulation to protect the wiring. So he has a whole bunch of these. That's Professor Ackerman. If you take one sensor and you connect it to one data logger, essentially a hard drive, and then you put them out in harm's way, sensor and data logger, well, as long as that data logger's got juice, got power, it's going to record every tenth of a second what the temperature is. So you put enough of those in harm's way, and what we lack in precision when we go outdoors, obviously we're giving up precision, right? It's not a totally controlled environment. But that's the point. What happens in the real world? Well, how do we make up on a scientific basis, like Denise knows, how do we make up what we might lack in precision? We make it up with volume, right? We just do a whole bunch. And if the data is scattered everywhere, it's not very reliable. If the data is tightly clustered, you start to get a sense that it's right. So that's the rough, the equipment. You'll get a quick look at the setup here. So this is one data logger being connected to one sensor, and then we'll show you the fire field and how we're putting them out there. Again, this is just a couple of experts in the business trying to figure out how we could measure how long these things last and how hot they get to stop the marketing that's going on. So we're putting them at center of, at that height, all of them at the same height. Why? Well, that's where people are, the center of your body mass, right? And so each one's going to be the same height. We're going to turn one in. There's two there, as you can see. And I'm turning one in toward the fuel source, so it'll measure the radiant from the plume that's going to continue to burn. And the other's turned out toward the flash. You know, the hydrocarbon drifts wherever it drifts, it flashes back. So you put enough of those in harm's way, and then the data logger is here, being wired to the post, and then that's insulation to protect the data logger, and then there's tin foil around that to radiant, to block the radiant. You put enough of those in harm's way, and wherever the wind's going, it's circumferential around the hazard. So here's the fuel source release. This, they call it a tree, but it's a pipe about the size and diameter of the top of the chair, or the seat of the chair, and it's about that high. And it's going to pour propane out at a massive rate. It's kind of cool. If anybody wants to see this live, by the way, we're going back in about 11 months. But it pours the propane out. It goes wherever it goes. And you have a set of sensors here. These are all doubles. One facing in toward the fuel source, one facing out toward wherever the flash is coming from. Wrong direction. Then there's a second set of sensors. And then a third set that you don't see out here are permanently lit fires. So what's going to happen is, because I can't reach up, let's say that the propane's drifting this way, and it gets to the flare that's lit here, and it ignites. What's it going to do? It's going to flash back. And these sensors will be in the way, and we'll be able to measure how long it lasts at any single location where you or your workers are standing. It wasn't rocket science. So in real life, you can see the tree right here. That's the propane source. You can see the permanently lit fires at the edge, and you can see all the sensors. We have a mannequin in there for scale. And then also because it was fun to throw non-FR and FR on him and see what happened. So there's the guy who's controlling the propane source. Here's a gas release. You see the propane coming out. It hasn't gotten to the torches yet, so it's not lit. So the three things that we're trying to answer here are, is this, in fact, a rapidly moving directional flame front? Meaning it's coming at you, right? Is it moving? And is it coming fast? And if it is, by the time it's on fire where you are, is it still on fire over here? And all that aside, the visuals are nice. Let's quantify it as well, both the duration and the heat. So if you're able to see this, I'm not sure you can in this lighting. You see there's two mannequins here, right? And here's the permanently lit fire. Are you able to see the fireball where there's fuel and fire? So it's on fire here. It's not on fire where our workers are yet, is it? By the time it's on fire back here, what do you suppose will be going on over here? Nothing. It's used up all the fuel, right? So we start to use the photos to get a feel, and I love this shot. In this case, the wind was gone the other way. So this is the permanently lit flare at the back that ignited it. In between the flare and the flame front is a big empty space. Why is it empty? Because the fire consumed all the fuel as it's moving. So you have a three-phase event. You have where the fire is, you have where the fire was and isn't anymore, and you have where the fire is going to be in a second if you don't get out of the way. These things do move, they move rapidly, they are directional, and that speed of movement is what lets single-layer secondary protective apparel, absent SCBAs and all, save people. So the visuals are nice, but the data is what really tells the story. Here's a perpendicular view. You'll see an ignition and a flashback. Now, you don't want to be standing in that, But how long did that last to go that whole 60 feet? 2 seconds. Way less than 3, right? And how long does it last if you're, let's say, standing leaning up against that pole? Well, it's a lot less than 2 seconds. So you start to get an idea from all these visuals that these are, in fact, directional, brief, and arguably, as a result, survivable in the right PPE. But I'm a big believer, and you'll hear me say this over and over, visuals are nice. We all respond to visuals. Data is boring. But what's really telling the story is the data. I mean, that's what counts here. We've got to have numbers. So real quick, you take what you saw in the lab and translate it outdoors. That's part of what I'm up to today, is continuing to translate what we see in the lab to what we see here to what you see. So this is a flammable garment that if you go to local working gear or whatever, you might well end up with, local Grainger. And even I was surprised at how easily this ignited. The first flash misses it, and then you see the swirl, the wind swirl it, and it comes and licks the back of the mannequin for maybe half a second. Take a look at the zipper in the front. Are you able to see smoke pouring out the zipper? You don't see fire in the front. You might conclude the front of this dude is not damaged. Smoke is not room temperature. You get second-degree burn at 140 F. Smoke is 350, depending on what this is. You're being boiled even where you don't see fire yet. Because the fire is doing what? It's looking for fuel and oxygen and rising, so it's rapid. It's looking for all that stuff inside. By the time I wander in to turn it around and show the camera, there's no back left, and now the front's completely gone too. There's almost nothing left to put out. So, again, that video is available for you. It's very, very low energy level necessary to do that. What about the data? This is the boring part, and I apologize, but the meat of the whole first half of the presentation, the proof, if you will, is here. So forget the center graph for a minute, if you would. Just focus on the ones around the edge. Each one of these is a single data logger, one of those little sensors, in one flash in one location. And the horizontal axis is time, and the vertical axis is heat flux. Look at that as energy or temperature if you want. It's not quite that, but basically. So what you have is there's no fire, no fire, no fire, no fire, fire, no fire. Simple enough, right? So for each one of those, you can see some of them are taller, some of them are fatter, because it's different each time. But if you take the width of the bottom of the V, they're essentially upside down Vs, right? The width of the bottom of that V, what is that? What is that? What is that? That's an exact quantification of how long the temperature was elevated right there. So finally, we can start to get at an answer. There were 36 of these sensors. We did 80-some flash fires in 01. We went back. That was natural gas. And then we said, hey, we need to do, that's lighter than air. We need to do heavier than air. And we went back in 2010 and 2012, and then a month ago. So we've got a lot of data. There's 300 and some flashes, 36 sensors, 1/10 of a second per, do the math, but a lot of data. And not a single, this is maybe the second most important thing I'll say in this hour, not a single one of these sensors of that gap, that measure of time, in a single flash, not one exceeded 3 seconds. We couldn't get 3 seconds. No matter how strong or weak the wind was, no matter what the humidity was, no matter how big the propane release was, we could not sustain one in a single location for anywhere near 3 seconds. So there's an obvious conclusion there. This is not the automatic end-all, be-all, but that's how hydrocarbons, it's a standard hydrocarbon. They all act more or less the same. What you have secondarily, the next big question is some people in the sales and marketing spin side of this business will say, well, what if the heat flux was 4 calories instead of 2 calories? Well, maybe if you just burn titanium or something, but hydrocarbons, 2 calories was chosen for a reason. That's highly representative of where hydrocarbons burn. But we can measure that too. The peak of each one of these graphs is the peak heat flux. Now, what's important is not peak. What's important is average. The peak, if it was really, really high for 1/1000 of a second, who cares? What's important is the average. So the center graph, as you might have already figured out, this red arrow, this blue bar here represents the heat flux of this one. This blue bar here represents the heat flux of this little one, and so on. Well, 84 kW, just almost 100 kW, is right about the dead center of that graph. Guess what those numbers average? Right around 84 kW. Now, I'm not cherry-picking data here. This is just random. Any random sampling you want to grab is more or less on target, because if you grab enough data, you end up to your mean, your average. But that and all the data that goes behind it, and a whole bunch of money on propane is expensive. You have no idea how expensive until you're buying it by the thousands of gallons instead of in those little Rhino containers. But anyhow, it wasn't cheap, but it was fun. And it did yield what we believe is absolutely meaningful and extrapolatable data. And the conclusion should be pretty evident. Now, what about this idea that it's a moving flame front? That if it's coming right at you and you're standing, let's say you're working naked, and I'm not advocating that, but if it burns your front, it probably didn't burn your back because it's a moving flame front. Well, we all intuitively know that, but I got chills when I first saw this data.